Now it so really happens is the moment you start displaying and working with all these wonderful things, there's still one thing which is remaining, that most of the times my evaluations are what we call as random. Okay, it's a public platform, I withdraw my statement. So sometimes some of my actions you don't know which one are what are random, or what we call as probabilistic in nature. So, for the same condition, for the same situation, for the same state, what I do, I randomly decide that. There's no logic behind it. It's all Mother Nature, because of which I'm making random decisions with some probability density function. So, let's really take an example, and this time, let's say all my actions are absolutely very simple. So at least where I am recording, it is horrendously cold. So all that I want to do is I want to have tea. So my behavior will be go to tea cellar. At tea cellar, I have tea, and once my tea is finished, then of course I go to office and work. Simple. And this is what I initially want to do. Well done, which by the way will never happen. I love this job. Our work can never get finished. The moment our work is finished, we create new work by giving new assignments to you people, which eventually we need to evaluate. Now, the problem is that you know that there are three places where I can have tea over here. The first place is the new canteen, which is not functioning, but it's just an example. The second place is, say, the old canteen, which is not working, but let's say it's working pre-COVID period. And the third place is, of course, the outside local store. So let's call it P1, P2, and P3. So let's model this thing up. So I again say my first behavior is go to P1, my second behavior is go to P2, and my third behavior is go to P3. And then of course, I have tea, I go to office and work, and I stop. And similarly with the other. Now, here things are a bit different. So here I say that mostly I'm a classy guy and I love the ambience of the new canteen. I'm a lazy guy, and you know that the old canteen is far off. And this is the best tea, I understand, as everybody knows it. I don't like the ambience. Point three. So these are probabilities. So for the first time, what I've done is I've added in nodes which incur probabilities. And that's very important because, any simulation, any multi-agent behavior, it really cannot happen unless there are stochastic elements attached to them. It just really cannot happen unless you have some stochasticity. And therefore, the same simulation, you run it 100 times, you'll get 100 different answers. Nothing in this world is deterministic. We never knew Corona would have happened. God is playing stochastic games with us. Nobody predicted that. No technology could do that because it's completely stochastic. It's completely complex. It's completely random. So, because it's completely random, it's completely stochastic. Therefore, we really do not know which route the program will take. Of course, we can have some probability measures and we can try to guess based on probabilities, but actually what happens, nobody knows. So, this is the first time that we have done selections based on some kind of probabilities attached to elements, and therefore let me take in one final example, and a very related example. And the example says that you are coming back from the pandemic and people have asked you to report to a warden, and one of the hostels has two wardens. So that's what you that's what you do. You say you go to hostel. When you at hostel, then you get to know that you need to, so that gets instructions. Only at the hostel gate we'll inform you you need to meet the warden first, and therefore what you do is, what's the warden selector? So you love the first warden, you hate the second one. So normally with a 0.9 probability you'll go with the first one, and with a 0.1 you'll go with the second one. So that's go to warden 1, that's go to warden 2. So with W1 and with W2, the next is common. So you just get permission, and once you get the permission, you go to hostel. And let's say you stop. So that's the one which has things which are stochastic in nature. Let's quickly take in, let's say, another one. So that's what happens every evening. You go to mess, action selector. So you decide whether you need to eat at mess or you need to go to a restaurant. In restaurant, of course, you have a restaurant selector. Now, I don't know the names of places where you people go. So let's say restaurant 1, restaurant 2, and as I've heard that you senior people mostly eat outside. Unless you don't have money, you are not getting stipend next year. And of course, this restaurant is very popular in contrast to this one or this one. So whether you actually eat at mess or one of these restaurants, it's completely stochastic in nature, and you decide that randomly. Nobody knows which algorithm you use, at least I don't know. So let's say that is absolutely, completely stochastic in nature. So we basically studied the behavioral with many examples. Finite state machine. Now, sometimes interesting things happen. I have a fire alarm, and you people would not be knowing, but in case of fire alarm, you stop everything, You stop everything and you move out for your own health and safety. Uh, at some parts of the world, which could be here, if there's a fire alarm, people will first think, why is the fire alarm giving a false alarm? We're so confident it cannot be real. So these are what are called as the external events. Now, one way to have external events is that from all actions which take time, now this one doesn't take time, this one doesn't take time, and the sensors don't take time. I actually say go to exit and go to exit and so on. Bad example because here, of course, you don't need to respond to external events, but then normally in a home and office scenario, you need to respond to all of them. So let's take one from here. So I add go to exit, go to exit, go to exit, go to exit, go to exit at all these things because poor peon. When there's fire alarm, he has to leave everything or she has to leave everything and just go to exit. So that's one way to do it, that in case of external events that you say that leave everything and say what the event does, or you can just specify a list of global rules or global events that when this happens, then your response should be so when this event happens, then this is the behavior. You need to leave everything. Whatever, wherever you are, you need to go to exit. Specifying the external events in the BFSM will make it cluttered. Remember, you need to specify it as an XML. Tell people make GUI tools. Actually, some open source people have made GUI tools. It's just not that they are not popular, or I don't know about them. Or you could have a list of external events where you just say that this external event happened. The external events may have additional criterion. So if this external events happened for everybody in any state which qualifies this criterion, this behavior has to be displayed, irrespective of everything. And then of course you could also have the external event release behaviors where you say that after the external event has ended, that means fire brigade came, blah blah blah, nothing happened, so you all go in. So for us, probably all the ruckus that you people create at the hostels are external events. We get a call, there's a problem, everybody come, and then all of us are running external event. There's a ruckus at the campus. We need to sort that out first. All other meetings to improve the institute, for increasing the international ranking, for doing international collaboration and quality R&D and quality teaching is gone. We need to respond to the external event. That's a priority. So that's the external event. Of course, I haven't mentioned the additional criterion, if any, and that's a behavior to be respond. Could be globally stored. And once this happens, then you can also have a release behavior now. Mostly in the schools, I will say, okay, write something formal program, pseudocode, algorithm design, blah, 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 that simulates this behavior, that behavior. The answer is always a BFSM, of course. It's formal. It's something that you can plug and play to a library and just click on simulate. It works beautifully. So it's stronger than pseudocode, it's stronger than programs, it's stronger than whatever. It has all the details. It's complete, it's exhaustive, which is wonderful. So I say in the question papers and assessments that say I want to create this type of simulation. There are 100 agents, 20 are working like this, 20 are working like that, 30 want to do this. And then this type of interesting things can happen when two agents interact with each other, and these guys are doing this and those guys are doing that. The program for everybody is a normal BFSM. Now, the problem is that most of the students who the schools are through in TOC and AI and everything. So in AI, of course, we talked about graphs in AI in multiple algorithms, and at each algorithm, many things changed. But one of the earliest and one of the most primitive and what intuitively comes in minds were the vertex was state where nothing changes, and the actions and the edges were actions where state changes. In a BFSM, the vertex are controllers or behaviors where some kind of a physical motion happens, and edges are transition conditions where no physical motion happens. So the controller gets offloaded and a new controller gets loaded, behavior gets offloaded and a new behavior gets loaded, but there's no physical motion. So the vertices produce the physical motion, the edges don't. And here, for a virtual robot, basically, for agent being planned, motion of virtual, because you know that in AI, when we are planning, nothing physically is going on. So motion of virtual agent happens. And if you see, they are both contradictory to each other. Physical motion is happening here, and at the vertex side in a BFSM, and the physical motion or the motion of the virtual ghost agent is happening at the edges here. At the vertices, no physical motion is happening, and here at the edges, no physical motion is happening. So if I just give you a question, same, you need to go to A, then you need to go to B, then you need to go to C. Of course, the correct answer is, in a BFSM, the correct answer is go to A, at A, go to B, at B, and go to C. However, if I just mess up the question, or if somebody just reads notes a couple of minutes before the assessment and just attempts the assessments, 90% cases because you worked too hard in AI, 90% of the people because you really learned AI. At this course, you become lazy, you are very eager and enthusiastic in AI. 90% of the students will actually be tempted because of the AI background to model it like this. Go to A, go to B, and go to C. Because in AI you've learned that edges is where the motion happens, and of course here you will say, in fact it'll become interesting because many people say source. In AI everything starts from source, and then you say at A, at B, and at C. So In AI versus in BFSM, things are actually exactly the opposite. Okay, you cannot stop here, of course. I should have drawn the last one as well. So the notations are exactly the opposite. The vertices have become edges, the edges have become vertices. And then I honestly have a terrible tough time because if somebody has written this and got full marks with a lot of appreciation and personal comments and likes, why should this guy not be awarded? It's exactly the same solution, which is what many people will come asking me. It's the same thing. So please make sure that if you are quoting something as a behavioral finite state machine for robotic programming only, for multi-agent programming only, multi-agent programming, we always just program one agent. The multi-agent collision avoidance and everything will be taken care of by the potential field. So the controllers are just the potential field. So whenever you're talking about multi-agent programming, whenever you're talking about robot programming, whenever you're using behavioral finite state machine as a tool, please make sure that the vertices are always controllers. So if you're using a library, the library will either ask a name of the controller so that it can look at the list of controllers and invoke that along with the parameter of the controller. So in terms of software implementation, of course, for all these go to A, go to B, go to C, the name of the controller is artificial potential field and the extra parameter is the goal name A, B, or C. Easiest example. So the moment you do this and you say source, now what will you specify as the name of the controller? Nothing. And therefore I have to take that difficult decision of giving no marks for this one and giving all marks for this one because every vertex is the name of a controller along with its parameters, and here you cannot do that. You cannot invoke controller. The edges are just conditions. You cannot specify the name of controllers for the edges. And therefore, for the edges, you just need to write down the conditions. And because you only need to write down what are the conditions where a transition happens, the library is only gonna check if that condition becomes true. If that condition becomes true, it's gonna invoke that transition. Of course, you have two special type of edges, one which were based on sensors, and there the sensor value is already available, and the second one which was based on probability, where the edge will have a attribute where you can specify the probability of that edge being selected, which makes programming robots really a fun task. So if you see beautiful simulations, multiple people going here, there, interacting between themselves, getting shopping, causing congestion, all those wonderful behaviors. So it's not difficult to program. You just write down a BFSM and you can simulate that till infinity. You can simulate the entire college life and the simulation will go upon till infinity or till 6 p.m. and all the agents will be doing what they do, which is to just go around and act as per the simulation. Even in the professional robots, a BFSM is running and the robot is always at some state of the BFSM. If you give an input, it has proper sensors through which it decides which transition happens or not. If you don't give an input, it knows exactly what to do, like go to the charger when the battery is really low, or to do an inspection at regular intervals, or to get coffee for me every 2 hours, or if I ask the robot to go from A to B to C to D and then come back and report me, or go to the lab and do the inspection and report to me. The robot does exactly that because all those behaviors are embedded, and based on the condition, the robot can decide which transition to invoke. Um, I would also encourage you to look at what is the difference without answering. And a rule-based system, which is also pretty interesting because classically everything was programmed like a rule-based system, including the modern computer vision applications, handwriting recognition, fingerprint matching. So the features ultimately make in some kind of rule, and then you say that, okay, if this one matches this one and this matches this one, and here I can have two kinds of variations. So if this matches either this or this, they've all lived in rules. BFSM is exactly the same thing. You've got a graph, and ultimately, this is a rule-based system. If this, then this, if this, then this, if this, then this, if this, then this. They look exactly the same. Now, BFSM is actually a generalized form of a rule-based system where your rules, which is this, become state-dependent. So the rules here will not be the rules here. And that's what makes rule-based expert system very difficult to program and maintain. BFSMs are just a graph, and it's usually fun to just play around and program them up, which is what makes great simulations, and which is also what makes in robots do some great stuff into the industry as well as for our own research. With this, I conclude this part of the lecture. Thank you.